All right, here comes another short for Foundations in Pre-Cal 10. This one builds off the slope idea, but we're going to tie it to a rate of change. So remember, this one includes units. Think rate of change, kilometers per hour, dollars per hour, liters per, or miles per liter, kilometers per liter, right? Fuel consumption. So anything we can tie units to becomes a rate of change, as long as it is a constant rate of change. And in high school math and physics, most of the time we were dealing with constant rates of change because fluctuating becomes incredibly complicated. So let's just look at here. We have a person runs a 400-meter race in 56 seconds. So you could look at this as a number of ways. You can start with, well, how far did they run at the beginning of the race? 0 meters. And what time was it at? 0 seconds, right? So if we think about it with respect to time and speed, here we have meters per second, which means our y values are meters and our x values are seconds. If we're thinking graphically, it's time down here and distance up here, which means if we're thinking about it as points, we're thinking about it as two coordinates. We have 0 for time, so 0 seconds, and 0 meters. And then when we're done, we have 56 seconds and we have 400 meters. Now, when you're starting at a 0-0 scenario, it's just a simple division question, because what we get is we get 400 minus 0 over 56 minus 0. So we get 400 meters over 56 seconds. And the units are going to tell us what we want. We want meters per second, so that's what we're staring at. And what this tells us 400 meters in 56 seconds. So break that down into 1 second by just dividing by 56. And in this case, what you end up with, 400 divided by 56, gives you 7.14 meters per 1 second. And this is where units come in handy. I made a big spiel in class, but units tell the story, because what you end up with here is 7.14 meters in 1 second. That's what that's telling you. If you multiply that by 400 meters, your units aren't canceling out, right? But if you multiply that by 56 seconds, well, seconds cancel with seconds, we're just left with meters. And 56 times 7.14 is 400 meters. So you know if you set an equation properly, if the units end up what you want them to be. It's really helpful there. So let's look at another one here. So we did this in class, but we're going to look at it here. There's lots happening. There's lots of information in this slide. Here you have a distance and a distance. You also have a time, 3 days. And then we have some information here on 63 liters to fill, and then also a cost equation. So lots happening, and we got to think about what is the rate of change we're looking for. So the first question says, determine the rate of gas consumption of the car. Gas consumption would be kilometers per liter. We want to know how far we go per liter, and we have some information on kilometers. Now, if you think about how we're going to set this up, okay, think about when the tank was full. So when the tank was full, we had 63 liters, and liters are going to be our X values because they're on the bottom, and our odometer read 86,347. When the tank was empty, it was 0, and the odometer read 86,721. So we've got ourselves 2 points that give us a distance over liters. So now we just do this equation. 86,721 minus 86,347 over 0 minus 63. Now you might be thinking here, well, how come I'm going to end up with a negative value? But if you think about it as a slope, yeah, you're going to have a negative value. But if you think about it as an actual scenario, you get negative 63 on the bottom. So 374 divided by 63 gives us negative 5.9, around there, kilometers per liter. So the fuel consumption isn't negative 5.9, but just think about what fuel consumption means. It means how much fuel you're using. So obviously your fuel is going to decrease, so you have a decreasing slope. But the fuel consumption of the vehicle, you would just say, is 5.9 kilometers per liter. So now the next one is determine the average rate of travel. So in this time, we want kilometers, but per time. And if we look at our time was in days. So here, our y values aren't going to change, right? Our kilometer value stays the same because we're still talking about the distance we went. So you can go all the way to the end of the question, and this doesn't change. We still have 374. We know that's going to be the difference between our odometer. But in this case, it just means I started at 0 days and I finished at 3 days. So it's 3 minus 0, which gives us 374 over 3. And that simplifies. I'll just draw it down here. And you can see your units here. We have kilometers and days. This bit belongs to this bit. So 374 divided by 3, 100, and we're going to round to 125 kilometers per day. So you get your average rate of travel, distance per day. Now, determine the cost of renting the car per day. Well, in this case, we need money. Now, we already know it's been 3 days, so we don't need to do any weird slope equations here, but we are going to have dollars per day. Now, we had $96 for the overall rental. So how much is that per day? Well, just divide it by 3 days, and we get that chunk comes out at $32 per day. Then we also need to consider the fact that it's 90 cents per liter. How much gas did we use? Well, we found out we used 63 liters. So 90 cents per liter, right? And here you can look at this units again, 90 cents per liter times 63 liters. My units cancel, and it cost me $56.70 for the whole trip. So we have to divide that by 3 because we want per day, and we get another $18.90. So add that to our 32, top left corner here, we get our total. It's going to cost us $32 a day in basic fee plus $18.90 a day, giving us a total of $50.90 per day. All right. So let's do one more here as a rate of change. So a plane at an altitude of 20,000 feet. So let's visualize this. All right, we got our beautiful drawing of a plane. That looks more like a person flying sideways. Let's make that more like a plane dorsal fin. We'll put some jet engine pieces on there. Okay, there's my plane. Nice fuselage. Okay, my plane is flying and it's up here at 20,000 feet. And it's been flying for 6 hours. So 6 hours actually becomes our 0 point. The entire flight time is 6 hours and 40 minutes. So that means when the plane has landed here on the ground, it's been 6 hours and 40 minutes. Now, don't get thrown off by the 6 hours. It's basically a bit of a red herring because how long was the descent of the flight? Well, the descent only took 40 minutes. Because if it was flying for 6 hours before it descended and then landed at 6:40, the descent took 40 minutes. Now we're looking for our descent in feet per minute. So if we start at 20,000 feet, we finish at 0 feet. So what our units look like, again, if we think about this, we have time and we have feet, right? So we have 0, 20,000 because we can think of that at 6 hours, sure, but as 0 minutes. And then here we have 40 minutes later, we're at 0 feet. 0 feet. So what does this look like for a slope? Well, y2 minus y1, 0 minus 20,000 over 40 minus 0 gives us negative 20,000 over 40. So we do that division, we get negative 500 feet per minute. And again, we can check that by taking our negative 500 feet per minute, multiplying it by 40 minutes, we get right back up to 20,000 feet. So that is our average rate of descent. All right. So that's how we tie units and rates to a slope. But again, it has to be a constant slope. There can be no fluctuations, otherwise the math breaks down, and that is where you get into more complicated mathematics and physics. This is just an average, linearly decreasing and increasing. Okay, great work. This ties to section 2.3, and I'll see you next time.